Assalamu alaikum. This is lecture 7 on modern control theory. We are discussing chapter 5 of the NICE's book. We covered in the lecture 6 the alternative representations of state space. So the summary of the alternative representation are actually given in this table. The phase variable, then we have parallel, cascade, controller canonical form, and observer canonical form. So their corresponding comparison has been given, the transfer function, signal flow graph, and as well as state space, static equations that is coming from the signal flow diagram. All these are actually summarized in this table with the 5 representation that we have learned. Now, my advice for you is to try to produce this table by yourself as a practice so that you can actually see different relationships among the forms that we have studied. Okay, so let us start formally the class with an example 5.8. A feedback control system is given, then we have to actually represent that feedback control system in state space, and they advise us to model the forward path transfer function in cascade form. So let's see what is the transfer function given. Example 5.8, a simple feedback transfer function with forward path gain, unity feedback. Forward path gain is 100, s plus 5 divided by s plus 2, s plus 3. Okay, so unity, negative unity feedback, CS. RS, this is error. So thing is that we have to represent it in state space, and forward path transfer function has to be modeled in cascade form. Okay, so let's start the example. So forward path, if we see what we have in the forward path is very simple. We have a gain of 100. It starts from error signal basically. Then we can, in the cascade form, we can say 1 by s plus 2. Then you have, you can take it one block, s plus 5 divided by s plus 3. Or if you want, you can actually take it as a 2 block as well, like this. You can take first 1 by s plus 3, then 1 s plus 5. So there is no point of actually using 2, because we know that they'll be linked with same variable, same state variable, that is x1. Okay, so x1 will be going forward path in this one, and the second one it will be going to the in the feedback in the first one, and since it is in the numerator, it will be going to the forward. Okay, so there is no point of creating 2 separate blocks, but if you feel it easy, then you can actually go for with 2 separate blocks. So let me show it with a single block, and basically E1. then we have a gain multiplied. Okay, then we have one integrator. We know how to represent it. The integrator 1 by s. Feedback is -2. Okay. Similarly, the second one is also another integrator. Then it goes to -3. And what about this s plus 5? Very simple idea. Actually, as you can see, this is your x1, this is your x2. So x2, now what you can write that cs by x1 s equal to nothing but s plus 5. So cs will be simply s into x1s plus 5x1s. So 5x1, so this is definitely your x1s. And also if you back from your different differentiation of it. Okay, so this is your output C of s. And it goes with 5x1, so simply 5x1 you can write in this way, and also feedback from the derivative of it, so with a gain of 1 because the coefficient here is 1, so this is 1. Okay, so we can just connect them with gain 1, and also from the input that is RS, it is going to be your with a magnitude of 100. Okay, so now we have to find out the x1 dot. So this is actually x1 dot, and this is our x2 dot. So what you can see that x1 dot equal to feedback is basically 3. Okay, so minus 3x1 plus x2. X2 is directly coming there. Then similarly, x2 dot equal to minus 2x2 plus 100. Now, one thing you have to be careful here is this is now actually E of s, isn't it? So E in the time given is E is nothing but R minus C. So basically reference input minus the output because unity feedback. So you can just simply write that thing. Also, what is our output? Output y equal to ct is equal to nothing but you can see that 5x1 plus plus, as you can see here, x2 is coming as well as this 3x1 is also coming. So the whole thing is actually fed back there. So we can say that plus x2 minus 3x1. So eventually 2x1 plus 2x1 plus x2. Now C is nothing but your output, and actually you can replace this C by this one. So you can write in this way that it is minus 2x2 and plus 100 R minus 100 2x1 plus x2. So if we simplify a bit, then we can see that minus 200 x1 minus 100 plus 2. So minus 102 x2 plus 100r. Okay, so all the equations are ready. And now we can just simply find out our state equation, that is x1 x2 dot definitely equal to, or you can write in this way, x dot equal to minus 3 1 minus 200 minus 10 202 x1 x2 plus 0 100 r, and the output equation y equal to 2 1 x1 x2. Okay, so we haven't actually completed the equation. So if you completed the signal flow graph, so if you want, you can actually complete the signal flow graph with the feedback as well. So just complete it, because we have just drawn from arrow, not the entire one. So what you can do is, you can say this is your RS. So RS minus C. So basically, you can just erase this one. I write it somewhere here. Okay, so R with magnitude 1 minus unity feedback with a negative, of course, negative unity feedback. So it goes on the output. Okay, so minus 1. So now the diagram signal flow, as far as the signal flow diagram is concerned, is complete. Okay, so this is the example how to do with it, deal with the modeling of your system, any system given, you can easily figure it out. There is one skill assessment exercise. I will ask you to actually solve that one. Already it's available in the internet, skill assessment exercise. Sorry. Skill assessment exercise, that is, I think number is 5.6. So you try to go and solve that one. It's relatively easier how to do with it. Now let us go to the next topic, that is similarity transformations, article 5.8. Okay, similarity transformation. So if you have one form, then how can we jump to the other form? So this is what is all about the similarity transform. So a review of a bit of a vector, how we present the vector. So say we have a system with two state variable in terms of, say, x1 and x2. And we know that the vector represented in terms of unit vector, say u x1, u x2. So say another subsystem we have. So because we have different form of representation, so this is another representation, another space, z1, and perpendicular to that one, that is z2. Okay, so a vector, a state is represented, say x is our state, which I think it will be better to represent with a different color. So a state is, say, in your state space. So there's two space here. One is x1, x2 space, and other one is z1, z2 space. So same vector, same state x can be actually represented by either of the two space, x1, x2 space, or z1, z2 space, or we can say that x can also be represented by z, but same thing can be represented different way, like the alternative forms that we have learned. So they eventually representing the same system, but they are represented in a different form. So this is what we are trying to realize, how actually can find this. So in terms of x, we can write the vector as x equal to اللهم رب هذه الدعوة التامة. Okay, so we can represent the unit basis function in the Z domain as well. Okay, and we can write the equation of x in this way, and we can write the equation of Z in this way. But eventually, one thing we have to keep in mind, they actually represent the same system. X and Z is same. So we are just trying to see how they can be actually transformed from one to another. So Z, as I said, the Z is nothing but Z1 UZI plus Z2 UZ2. So UZ1 and Z2 are the bases. So now we can also represent the basis UZ1 in terms of the basis vector of the X. That is, say, P11 UX1 plus P21 UX2. So what we are trying to do is, in terms of X1 and X2, we are writing this basis vector. Similarly, in terms of X1 and X2, we are trying to write the other basis vector. So similarly, we can write YZ2 equal to P12 UX1 plus P22 UX2. Now these basis values, if we plug into this equation, then what we are going to get is Z1 Z1 and P11 UX1 plus Z1 P21 UX2 plus Z2 P12 UX1 plus Z2 P22 UX2. Now UX1 and UX2, if we take common, then what we find is Z1 P11 plus Z2 P12, that is UX1 multiplied by ux1 plus z1 p 21 plus z2 p 22 ux2. Now this one, as you can see that we already said that x and the z are the same thing, so z can be equal to x equal to this, and we know that how to represent the x equal to x1 ux1 plus x2 ux2. So we can easily say this is nothing but your x1, this is nothing but x2. So x equal to x1, x2, isn't it? So write that z1 p11, z2 p12, z1 p21, z2 p22. Okay, so now okay, so this is a summation. Okay, so this is your x1 and this is your x2. Now, what can we write is in terms of if you separate the variables, so then you have p11, p12, p21, p22. Then you have z1, z2. So this is a matrix P and this is your matrix Z, and which is actually equal to your matrix X. So you can easily find out the relationship between X and Z with multiplying with this vector P, which is nothing but actually the coefficients of your, this column is nothing but the coefficients, coordinates of your U, Z, I, and this is the coordinates of U, Z2. So you can say that P is nothing but the coordinates of UZ1 and coordinates of UZ2. And also, since P is known, you can easily find out the inverse P as well. So you can say that Z can be written as P inverse X. So bottom line is finding the P. And once we know what is P, which is the coefficient coordinates of your UZ1 and Z2, if we know that, we can easily represent the system in this way. Okay, so there is one example given in the appendix. It's up to you if you want to go about it, but it's not that important in my understanding because of the fact that we're just reviewing the thing. So another way to see the thing that we have stated here is that the coordinates of UZ1 and coordinates of UZ1, Z2 are the columns of your P matrix. So that can also be verified using this one, P equal to Z1, UZ1 plus Z2, UZ2. So we know that X equal to actually Z, so Z1, UZ1 plus Z2, UZ2. We can easily write in the matrix from something like this, U Z1, Z2, and Z1 and Z2. So what we know is that P and Z equals PZ is equal to your X. So we can easily, a simple short way to see that actually the coordinates of UZ1 and UZ2 is actually forming the matrix P. So it's not that complicated, rather we should keep it as simple as possible. Now, if we have the state equation, the way we represent the state equation, that is x dot equal to ax plus bu, and output equation y equal to cx plus du. So what are the new things that we have obtained now is x equal to pz. So you can say that x dot equal to pz dot. So if we have these two and plug into this equation, what we find is pz dot equal to a pz plus bu. And in the output equation, y equal to c pz plus du. Okay, so now if you want to represent the system into z domain, so it has to be z dot equal to, take the inverse Laplace, that is inverse matrix AP z plus p inverse bu equal to y equal to cpz plus du. So what you can see here, this with the new system that we are obtaining here, in this case, your system matrix is A is represented by this one. So this is your new A matrix. This is your new B matrix. And this is your new C matrix. D is remaining as it is, so it's unchanged. Okay, now our concern is whether the transfer function is remaining same or not. So it may happen that with the equation that we have, the new system that we're having, whether that is producing the same transfer function or not. So previously, what we have seen is the output function, transfer function TS, YS by US, output by input was C SI minus A inverse B plus D. So this was the scenario. Now, as we have seen that the system has been changed, so the new parameters, if we introduce, C will be replaced by CP, and SI remaining as it is. The A is now replaced by new A, that is P inverse AP, and then inverse B plus D. So, sorry, the D is unchanged, but B is changed. B is actually P inverse B. Okay, so now whether this gives you the same function or not, that is a concern, and we try to prove that as well. That is actually the so for that we have to use one identity of a matrix, that is Mn. If both of them are inverse, so they are actually reversed while they have individual inverse. It means M was first, N was second. These are very matrix, so you cannot just alter. So Mn, if their whole thing is multiplication of the whole thing is, you have to take the inverse of that. Then wherever you're taking individual inverse, then N will come first, then the N. So this identity we have to use to simplify this one. So as you can see, there is two inverse matrix, this one, as well as the P inverse, small p inverse. So now if you want to take under a common inverse, then P will be coming first, then your the other big one will be going. So CP, then P coming first, then you have SI minus P inverse AP. Okay, then whole thing is actually inverse B plus D. Okay, so now can we simplify the thing a bit? Not yet. So what we can do is we can use a bit of trick. The P can be written as P inverse to the inverse. Okay, so because we want to insert this P into this one, in this big one. So now P SI minus P inverse AP inverse B plus D. So now this thing is also inverse, this thing is also inverse. So if you now try to plug it in, so we actually have to reverse the direction as per this identity. So this one will be going last and this one will be going first. So see, the whole thing is basically P SI minus P inverse AP. Then you have P inverse. Then you have B plus D. So the same identity we have to use twice to simplify the thing. Now, if you multiply this P with the parameters that you can see, it will be now it will be just multiplied with this one, so it will be P inverse simply. So P into S into P inverse, and P and the P inverse, they will be cancelling each other, so it will be plus minus P inverse A. Then we have one thing we forgot is this inverse here. So overall there is inverse B plus D. Now, since S is just a constant, so we can easily multiply S P P inverse minus P P inverse A inverse B plus D. So what you can see is, so now the PP is cancelling each other, so it will be left with this just identity matrix minus this PP's identity. So we multiply with A will give you just A, and minus inverse B plus T. So wherever we started, TS equal to YS by US, we actually end up with the same thing. So basically, both the transformations, they are actually representing the same transfer function. So these are not complicated at all. So even though they look different in the matrix form, eventually they give us the same transfer function. Okay, so now let us look at the next idea, that is, so whatever so far we have learned or summarized from this background is that for the similarity transformation, if x dot equal to ax plus bu, something that we have with output equal to cx plus du. So summary is that if you want to transform it to z, then it will be something like this: z transform equal to p inverse a p z plus p inverse b u y equal to cpz and du. So these are not changing at all. Okay, and also whatever we have figured out is P is nothing but the coordinates of the Z1 and Z2, UZ1 and UZ2, and which is P11, P12, P21, P22. And finally, what we have seen is that X equal to that P matrix, that is P11, P12, P21, P22 with your Z1, Z2. And we simply have written in a smaller version, something like this. And that gives us the way to represent the Z in this way: Z equal to P inverse X. Okay, so this is two simple things. Now what we have to do is simply find out what is P. So once we can find out the P, so we can easily inverse it to find out the Z matrix as well. Okay, so with these ideas, let us try to solve another problem, try to apply these ideas into a problem. So, example 5.9. One system is given x dot equal to 0, 1, 0, 0, 0, 1. And by looking at this form, you can easily see this is nothing but in the phase variable form. 0, 0, 1, u. And our output, since it is phase variable form, so 1, 0, 0. So we have to find out the representation in terms of Z, where the relationships with the X and the Z are given. So these are also given. Z1 equal to 2x1, Z2 equal to 3x1 plus 2x2, and Z3 equal to x1 plus 4x2 plus 5x3. Okay, so these are given, so we write out in terms of the Z parameters. That means Z dot equal to something and Y equal to in terms of Z. So this is what we are looking for. So first thing first, we have to find out the P matrix, so whether we can find it. So from this given values, you can easily see that Z equal to, you can write in this way, 2, 0, 0, 3, 2, 0, 1, 4, 5, and these are X parameters, so X1, X2, X3. So we know that Z equal to P inverse X. So what you can see that this matrix that we have obtained from the relationship that has been given is actually our P inverse. So once we have the P inverse, we can easily find out what will be. You take another inverse of P inverse, that will give you P. So P inverse AP we have to figure out, and that is 2, 0, 0, 3, 2, 0, 1, 4, 5. I'm letting it to you to find out. System matrix we already know, 0, 1, 0, 0, 0, 1, minus 2, minus 5, minus 7. So I'm just letting you to figure out what is the value of P. So just take an inverse matrix. You may use the calculator, or you can use the formal handed methods. So it's up to you. And now, once you have all these metrics, you just simply multiply them together to find out this matrix, that is minus 1.510 minus 1.25, 0.7, 0.4, and minus 2.5, 0.4, minus 6.2. So this is basically your NU. So the theory was a bit complicated, but at the end, as we can see, that the math problems are not that complicated once the relationship has been provided, basically. So the next parameter that you will find is P inverse B. So P inverse is already given 2, 0, 0, 3, 2, 0, 1, 4, 5, and B is also provided 0, 0, 1. So if you just multiply, as you can see, the last column will be just existent, so 0, 0, 5. Okay. Now, as well as CP, the P is already, you are supposed to figure out, so 1, 0, 0, and then you have this 0.500 minus 0.75, 0.50, 0.5 minus 0.4, 0.2. Just multiply, as you can see. This will give you simply the first parameter with the existing, rest of them which you're canceling out. So it will give you 0.500. Okay, so now new system, we already know how to represent Z dot equal to basically P inverse AP Z plus, that is the matrix that we calculated, and then you have P inverse B. This is what is also calculated, U, and then you have Y equal to CP Z plus D. D is unchanged, so we don't have to. So just put the values. So the new system that we are going to get finally is Z dot equal to minus 1.510 minus 1.25, 0.7, 0.4, 0.5 minus 0.4, 0.2. This is your z plus 0.05 u and y equal to 0.500 z. Okay, so this is a simple idea. Now, next thing is diagonalizing system matrix. So if your system matrix is given, then how can we diagonalize the system matrix? So basically what we're trying to find is say 0, 1, 0, 0, 0, 1, then you have I think minus 9, minus 26, minus 24. So this was your system matrix, one of the example. So how can we actually find a system matrix, new system matrix that will give us diagonal values only? Okay. So the other, and as we have seen that the diagonal matrix is having the advantage of decoupling. So basically we can separate the variables and that is easy to solve. So since we have seen that in between two different mode like X and Z, the only thing that matters is P. So if you can find out a P that can relate this matrix with that one, then you can easily we will convert that system matrix into a diagonal system. So appropriate values of P, if you can find, then you can find out the new Z equal to P inverse A P Z. So basically this will give you a new matrix that will have only diagonal parameters. So for doing that, we have to know about the eigenvalues. So definition of eigenvector and eigenvalues will be helpful. So we know that if any matrix X, if we want to find out the eigenvector of the matrix A, that actually if all the vectors that is transformed by the system matrix, what does it mean is xi is a vector. If xi is transformed by the system matrix, and it gives a linear combination. This is just a scalar value. This one is a scalar with xi. Okay, so this one is this relationship. If it holds true, then we call that xi are the eigenvectors. Vectors of matrix A. So what does it mean is that any vector that is actually transformed by the system matrix and produces a linear combination of those vectors, then these vectors xi's are called actually eigenvectors, and the lambda, those values are called actually eigenvalue. So xi is a vector, eigenvector, and the lambda is eigenvalues. Graphically, what it means is basically X. So if you have a matrix X and that is multiplied by a, if you have a vector X, this is your X, and it is multiplied by A, then it should be in the same line, maybe smaller, squeezed, or maybe expanded, but it has to be on the collinear. But if you have a matrix, if you have a vector, and that has been multiplied with your matrix A and it goes somewhere else, not collinear, okay? So that in that case, this is the X, this X is not eigenvector. Okay, so in this case, X is eigenvector. Okay, so this is the graphical meaning of eigenvector. Now, mathematically, let us try to figure out the eigenvector. Okay, so what you can see is that the initial equation AXI was equal to lambda xi. So as I already said, A is matrix, X is a vector, lambda is a magnitude simply. So if we take a the other side, zero matrix, zero, obviously a vector, lambda I minus A into xi. Okay, so this is what we get. Now, by definition, x cannot be zero because if x is zero, then it is always true, isn't it? So if x is zero, this side is zero, this side is zero, so it's true. So x cannot be zero by definition. So how can we prove that x cannot be zero? So if you further simplify, you can see that xi equal to actually lambda I minus a inverse into zero. Okay, so it seems now the inverse matrix can be written as adjacent lambda I minus a divided by determinant of lambda I minus a into zero. Okay, so what you can see here is that if xi is zero, then it doesn't hold true. So xi cannot be zero. But only possible thing is if determinant lambda del I minus a is zero, then 0 by 0 is undefined. So xi can have some other values than 0. Otherwise, in every case, because of this 0, xi will be 0. So it's not true. So for that one, what we have to do is we have to set determinant of lambda I minus a equal to 0, and that will give us actually the eigenvalues. Okay, so this is how to figure out the eigenvalues and the so mathematically. So with the example, it will be more simple for you to understand. Let us go with one. The theory seems a bit complicated, but if you go into the mathematics, you'll see that those are not that complicated. So A matrix is given -3, 1, 1, -3. Okay, so we have to find out okay. So one thing I actually forgot to tell you is that why we are interested about this eigenvectors. It is been seen that if the eigenvectors are combined forming the P matrix, that is x1, x2, x3 eigenvectors. Okay, so forming the P and that corresponding P inverse AP will actually give us a diagonal matrix. Okay, so this is by observation. So that is why we're interested about the eigenvectors. We'll try to figure out the eigenvectors, and that eigenvectors will form us the P matrix, and eventually then P inverse AP will give us a diagonal matrix. So let's try to prove all this using one example. So first of all, there is two examples, example 5.10 and 5.12. They're combined together, they're combined together to complete this solution. Now, first one, 10 is matrix is given. We have to find out the determinant, and corresponding, we have to find out the eigenvectors. So our objective from this one is finding eigenvector. Okay, so let's do that. So first of all, we have to find out the eigen values. So eigenvalues will given from lambda I minus a determinant of this. So basically lambda times 1001 minus 3 minus 3, 1 minus 3. So this will give us lambda 0, lambda minus 3, 1, 1 minus 3. So if we simplify a bit, it will become lambda plus 3 minus 1 minus 1 lambda plus 3. So we just multiply together and it will give us cross multiply, and then it will use lambda plus 3 whole square minus 1. So basically lambda square plus 6 lambda plus 9 minus 1 is basically 8. Now if we set it equal to 0, then you can find that lambda 1, 2, the two eigenvalues is basically minus 2 and minus 4. So to find out the eigenmetrics, the same equation that we are given, AXI equal to lambda XI. So our X is definitely, we have two system matrix is something like this, minus 3, 1, 1, minus 3. So we need two parameters in X. So basically X1 and X2 equal to the value, that is the first value if we take minus 2. So first value we are taking minus 2. And then minus 2 into X1 and X2. Now if you solve this one, then we're going to get two equations. Equations are, okay, sorry about this change. So actually went to the top. So now go back to the point where we are discussing. Okay, so it will give us two equations. The first equation is x1 minus 3 x1 plus x2 equal to minus 2 x1. So minus minus going here. So basically x1 plus x2 is equal to 0. So this will give us x1 equal to x2. Same from this is from the first one, but from the second one also you can see, and for your reference, actually they will give the same result. Okay, so 3x2 equal to minus 2x2. So basically, as you can see, x1 equal to again x2. So it will give the same result. So now you have infinite number of choices for your eigenvector. So what you can say that the first set of eigenvector is basically CC. So whatever the relation, whatever the first value x1, the other value is also same, x1 equal to x2. So it can be 1, 1, it can be 2, 2, whatever equal values, all of them will be actually representing the eigenvector. So for simplicity, just take one more. Okay, now take the value minus 4. So the minus 4 eigenvalue, if you take, again, same thing, a matrix that is 1, 3, or 1, 1 minus 3. Then you have x1, x2, okay, equal to minus 4. Then you have x1, x2. Now the relationship that we can find now, minus 3 x1 plus x2 equal to minus 4 x1. So basically x1 plus x2 equal to 0. So as you can see, we can easily find out x2 equal to minus x1. So whatever the value of x1 you take, and the negative of that thing will be your x2. So in this case, again, you have infinite number of choices. We can call this one as x2, say x2 equal to x equal to c minus c. So you can take 1 minus 1, 2, or 2 minus 2, 3 minus 2, whatever it is. So this is how you can find out the eigenvector. So two eigenvectors we found for eigenvalues -2, we have found that x equal to 1 minus 1. And for the other one, we have find that x equal to, sorry, first one was actually 1, 1, and the other one. This is one of the choice, of course, you have to keep in mind. So this is another one. Now, what we are trying to say that if you want to find out a diagonal system matrix, we say that if we take these two eigenvectors as your P matrix, that is 1, 1, which is x1, and 1, 2, which 1 minus 1. 1 minus 1, which is your x2. So this is corresponding to -2 eigenvalue. This is corresponding to -4 eigenvalue. So if you use this one and then try to transform your A matrix into P inverse AP matrix, then this will give you a diagonal matrix. Okay, so let's prove that. So our A matrix of the given system was basically -3, 1, 1, -3. So actually in example 5.11, they have solved the whole system for a whole system, and they have seen the figure out Z inverse equal to matrix into Z, new A matrix into Z plus new B matrix into U, then Y equal to a new C matrix into Z. Okay, so this is what they have done, but I'm just showing you because already a long time has been elapsed, so I'm just simply showing you that whether the new P matrix that we have obtained is actually diagonalizing the system matrix into new form. So basically P inverse AP, yeah, I'll let you do the whole problem solving. So again, in the P inverse, you have to calculate is half minus half. This is P inverse, A already given, so -3, 1, 1, -3, and the P matrix 1, 1, 1, -1. So if you just multiply them all of them together, the result will be -2, 0, and 0, -4. So as you can see, the new A matrix or system matrix is a diagonal matrix. And also eigenvalues or in terms, the poles of the system is actually coming the diagonal. So your task is to complete example 5.11 and also solve skill assessment exercise 5.7. Okay, so see you in the next class, inshallah.